This is an orbit problem. We're going to find the height of a satellite, and then we're also going to find the period of the satellite's orbit. Okay, this problem states a satellite travels 3,600 meters per second in orbit around the Earth. Find the distance. Well, part A is find the distance from Earth's surface to the satellite. Part B is find the period of the orbit, the satellite's orbit. This is the free body diagram of the problem. Right here you can see the satellite, and then we have an acceleration vector right here, and we have a velocity right here. Okay, and what we're going to try to do is we're going to find the distance from the surface to the orbit, and also the time it takes to complete, for the satellite to complete one revolution, which is the period. So next we're going to look at how to set this up and the formulas and the variables involved. Okay, we're going to identify the formulas, and then from those formulas we'll derive an equation. So for this problem we're going to need three formulas. First would be the universal law of gravity, and that states that the force is equal to the gravitational constant G times the quantity of one mass times another mass divided by the distance between those two masses squared, or the radius squared. The second is just Newton's second law, and we're going to manipulate it a little bit, which is force equals mass times acceleration, and that's going to be the mass of the satellite, and then that'll be centripetal acceleration. And then third, we're going to need the formula for centripetal acceleration, and that's the tangential velocity squared divided by the radius. And we start with the second equation right here, and that goes right here. And then we take the first part, the first equation, and that goes right here. And then you can see that we're going to substitute in this third equation for the AC, and that goes right here as we derive it. And overall, this general part right here is what we're going to use to solve this problem. So we'll continue next on to manipulating just this part that I circled in green right here. Okay, here we're going to reduce an isolated variable right here, and the variable we're going to isolate is r. And we're going to first cancel out the mass of the satellite. We do not need it. It's on both sides, it'll cancel. Next, we're going to multiply both sides by r squared, and that'll cancel out that. And then we're going to multiply both sides by 1 over v squared, and that'll cancel that. And we should get this bottom part, r squared over r equals r. So we went ahead and isolated that variable, and we get this right here, this part, and we can plug in some values for here, for this part right here specifically, and we'll get what r is, because we know what me would be the mass of the earth, v of t squared is given in the problem, and g is a gravitational constant. So just a short little part right there. Okay, now we're to the part where we're going to calculate r. And by doing that, we'll give you a numerical value for the distance from the surface to the orbit. So we'll start here with g. G is given right here. That's a gravitational constant. You can look it up. Another one you can look up is the mass of the earth. You can Google it or look in your physics book, or various other ways. The tangential velocity right here is given in the problem, and you can also look up the radius of the earth. That's all given. So if we sub in g right here, and then we sub in me right here, and then we sub in v of t right here, we'll develop this expression right here. And that you can put in your calculator, and you should get a number about like this. And that's going to give you the distance from the orbit to the center of the Earth. But we don't want to the center of the Earth, we want from the surface of the Earth. So what we do is we subtract the radius of the Earth from this general radius, and that'll give us our radius from the surface to the orbit. And all you need to do for that is sub in this with that. We just solved for the r right here, and subtract those two, and you should get this number right here, which is part A of the problem. And with this, we can start to work on the next part. Okay, now it's time to solve part B, which is pretty easy because we did all the hard work to find what that radius was. And this is find the period. The period is the time it takes to make one orbit, which is easily put as circumference divided by the speed. Now you're going to use the r you found, which is the radius of the orbit, not the distance from the surface to the center. You want the distance from the surface to the orbit. You want the distance from the orbit to the center of the Earth. That's what you want to put for your r right here, which is the first part you found previously. So you put this in your calculator right here. You should get something like this, which is 52,000 seconds, which isn't really too helpful. You know, it's better to put something like that in hours. It's going to take about 14 hours to 14 and a half hours to orbit. You might get different numbers based on estimation, but it should be about this. And then you found the period. Next, we're just going to kind of look onto the overall general workings of how this would work with different numbers and different values, and just kind of look at an overall of how this problem kind of works. Okay, we're coming to an end for this problem. Just to put a quick note, you know, how this problem works and some things I noticed. First is that the greater the speed, the smaller the radius. So, understand that the satellite is in orbit. So that means it's really not going faster or slower, and its orbit is dependent upon a radius. So there's no acceleration going on. It's just kind of was sitting out there, left at a certain distance from the Earth, and it's traveling based on that acceleration vector, which holds it in orbit. So as the speed increases, you can see the speed is down here. If that increases, this is going to get smaller. This radius is going to get smaller. The speed is also squared, so that definitely means the speed goes up, because the mass of the Earth isn't going to change and the g isn't going to change. So as the speed increases, the radius is just going to get smaller. Now, next for that part B, you can also notice that if the speed decreases, the radius is going to get larger. Just to note that. So as this gets smaller, this is going to get bigger. So just kind of recognize that, and that's kind of how the general idea of this is. If you're given a speed and you want to know how far it is, how far its orbit is out based on its speed. And you can go the other way. If you know how far it is out, you can kind of judge, well, how fast it is. You could just solve for the speed if you had the radius. But it happens several different ways. And the next part for part B is that the greater the orbit speed, the shorter the period. Now, this isn't only just because it's traveling faster, okay, that, you know, the thing is, it'll have a smaller radius, and it'll be traveling faster. So, it's proportional to its radius over the speed. So, the speed's greater, which makes it smaller, but the radius will also decrease. So, and that when you do that, it's going faster, plus it's going in a smaller distance, which makes the period much shorter. And reverse for the other way. As the speed decreases, it's going to travel. The period's going to take much longer, and that's just not only because it's going faster around. It's also changing the distance it's traveling too. So those are just some simple operations or observations about, you know, the general ideas behind this problem. And this will get into a greater depth of topics with Kepler's laws and, you know, angular acceleration, angular velocity, just how general things are when they spin and go around in circles. But I'll talk about those probably in a later video. Thank you very much. Yeah, thank you again. And I got this from a physics book, an old physics book. This problem. I changed the numbers around, but problems still work the same. Thank you, and let me know if I have made any mistakes or if you want me to solve a problem. I'd really appreciate you if you'd leave a comment or subscribe or like the video if you liked it, or if it helped you, or if you have any suggestions for me. Thank you.